My name is Richard Uhler. I'm a software engineer on the Android runtime team. I've spent the last 3 years trying to better understand memory use on Android. And more recently, I've been working with first-party app developers to tackle the challenges of evaluating and improving Android memory use. It's great to see so many of you here interested in Android memory use. To start off, why should you, as an app developer, care about memory use? For me, it's really about the Android ecosystem, the ecosystem of applications, of devices, and of the users of those devices. And where memory comes into play is not so much for the premium devices, where you have a lot of memory available, but much more for the entry-level devices. Because these devices need a decent selection of low-memory apps to work well. If application memory use and requirements grow, then the entry-level devices won't work as well. If they don't work as well, OEMs will not want to produce these devices. And if they don't produce these devices, well, we're kind of excluding a bunch of users from our Android ecosystem. And that's a bad thing. So app developers have a role to play when they're developing their applications to do whatever they can to be efficient in your memory use, to reduce your memory use, keep it from growing too much, so that we have a nice selection of low-memory applications, so that entry-level devices behave well, they work well. And if that happens, OEMs will produce these devices, and we can put them in the hands of users to use our applications. So in this talk, I'm going to talk about 3 broad categories, 3 areas. First, I'll talk about the mechanisms that come into play on an Android device when it's running low on memory, and how that impacts the user. I'll talk about how we evaluate an application's memory impact, and in particular, some very important factors to be aware of that come into play with that. And third, I will give you some tips for how to reduce your application's memory impact, especially given that a lot of the allocations going on in your application originate deep within the Android stack on which it's running. OK, let's start. What happens on a device when it's running low on memory? Well, memory on device, physical memory on device, is organized or grouped into pages. And each page is typically around 4 kilobytes. Different pages can be used for different things. So pages can be used pages. These are pages that are actively being used by processes. They can be cached pages. These are pages of memory that are being used by processes, but the data they contain also lives somewhere on the device storage, which means we can sometimes reclaim these pages. And then there might be free pages of memory sitting on the device that you're not using. So what I've done is I took a 2 gigabyte device, and I started it doing nothing. So at the very beginning of time, the runtime's not running. And then I started using it more and more. So lots of different applications, exercising them, which has the effect of using more and more memory on the device over time. So we can see at the beginning, the flat line there is before I started the runtime. Then I start the runtime up. There's plenty of free memory available on the device. And this is a happy device, because if an application needs more memory, the kernel can satisfy that request right away from the free memory. Over time, as you use more memory, the free memory gets exhausted. It goes down. And to avoid very bad things from happening, the Linux kernel has this mechanism that kicks in called kswapd. And kswapd's job is to find more free memory. This kicks in when the free memory goes below what I'm calling here the kswapd threshold. And the main mechanism that kswapd uses to find more free memory is to reclaim cached pages. Now, if an app goes to access a cached page or memory that was on a cached page that's been reclaimed, it's going to take a little extra time to reload that data from device storage. But probably the user's not going to be noticing this, so that's OK. Now, as I exercise more and more applications, they use more memory. The number of cached pages is going to fall as kswapd starts to reclaim them. If it gets too low, there's too few cached pages, then the device can start to thrash. And this is a very bad thing because it basically the device will completely lock up. So on Android, we have a mechanism which is called the low memory killer that kicks in when the amount of cached memory falls too low. And the way this works is low memory killer is going to pick a process on the device, and it's going to kill it, and it's going to get back all the memory that that process was using. Now, this is an unhappy state to be in, especially if the low memory killer kills a process that the user cares about. So let me go through and tell you a little bit more about how the low memory killer decides what to kill. Android keeps track of the processes that are running on the device, and it keeps them in a priority order. So the highest priority processes are native processes. These are ones that come with Linux, things like init, kswapd, which I told you about, daemons like netd, logd, and Android-specific daemons, adbd, installd, basically any native process that's running is categorized into this. The next highest priority process we have is the system server, which is maintaining this list, followed by what are known as persistent processes. These are kind of core functionality, so telephony, NFC, SMS, those kinds of things. Next, we have the foreground app. So this is going to be the application that the user is directly interacting with. In this case, perhaps the user is viewing a web page, so they're interacting with the Chrome app. Next in priority are what are called perceptible or visible processes. These are not processes the user is directly interacting with, but perceptible in some way. So for instance, if you have a search process, maybe it has a little bit of UI on the screen. Or if the user is listening to music in the background, then they can hear that music through their headphones. They can perceive it. After the perceptible apps, we have services. These are services started by applications for things like syncing or uploading, downloading from cloud. And then we have the home app. This is what you get when you hit the home button. It often hosts your wallpaper if you have something there. So in addition to these running processes, we also keep track of what the previous application the user used was. So maybe they're using this red app, your red app, and it brings them to Chrome with a link. Then when they've switched to Chrome, that app is going to be the previous app. And we also keep in memory a bunch of other processes, which are cached applications the user used before. Some of them maybe recently, some of them not for a little bit of a while. I want to point out here that these cached processes, when I use the term cached, this is a different use of the term cached than the cached memory pages I was talking about previously. OK, so the reason we keep around previous and cached processes is because if a user wants to switch to one of these applications and say they want to switch to the previous application, it's very quick to switch to that. Oh, I should say this is for a device in a normal memory state. So if you want to switch to a previous application, that's very quick. But also, if you want to switch to an application that happens to be in a cache process, that's very quick to do because it's already in memory. If we step back, though, and say, well, what happens when the device is low on memory? In that case, we could imagine the memory used by the running applications is growing. The number of cache pages drops below the low memory killer threshold. The low memory killer now has to come in and kill something to free up some memory. Well, it's going to start killing from the bottom of this list. So maybe it kills this blue application. That's gone. We get some more memory back for the applications that are still running. But if the user now wants to switch and start using that blue application, it's not cached any longer. It means it's going to take a noticeably long time to launch that application. It could be 2 or 3 seconds, and maybe it's lost some state. So this is where the user first starts to really feel, oh, something's going on here that's making things slower. If the processes that are running continue to use more memory, so we get under more memory pressure, low memory killer is going to start to kill more cache processes. If they continue to grow more and more, until eventually there's only a few cache processes left. At this point, we say the device memory status is critical. This is a very bad place to be. If the running processes continue to use more memory, though, the low memory killer is going to have to kill more processes. Eventually, it's going to end up killing the home app. At this point, the user's going to ask, well, hey, what just happened to my wallpaper? Because when they go home, it's going to be a black screen for a few seconds before the wallpaper starts up again. If it's even worse, maybe a perceptible process is killed. The user's going to say, hey, what just happened to my music? I was listening and it just stopped. Really bad case, the foreground app is killed. To the user, this looks like the app crashed. And the most extreme case you can get into for a low memory killer, basically, it needs to kill the system server. This looks like your phone is rebooted. So these are all very visible impacts of what happens when a device is running low on memory. And it's not a good user experience when this is happening on your device. Okay, I want to go back to this graph that I was showing before about what happens to the memory pages on the device as you use more memory. This was a 2 GB device. What do you think it looks like, this graph, for a 512 MB device? I'm going to give you a few seconds to think about that. You have an idea what it looks like? So I tried it for a 512 MB device. Same thing, start the runtime, use more memory, and it looks something like this. So because there's so little memory available at the beginning, there's very few free pages that we can use up before the kswapd has to kick in. And then there's very few cache pages we can reclaim before the low memory killer is needed to start killing things. And so you can imagine if you have this device and the low memory killer is always active, it's always killing processes, and it leads to this bad user experience, then maybe OEMs are not going to be too interested in shipping this device because, well, it just doesn't work well. And that gets back to the ecosystem challenges I mentioned in the beginning. So this is why we care about memory. Now, how do we figure out how much memory an application is used? How do we know your application's memory impact? I told you that memory on device is broken down into pages. The Linux kernel is going to keep track for each process running on the device which pages it's using. So maybe we have a system process, Google Play Services process, a couple apps running on a device. We want to know each of their memory impacts. Well, just count up the number of pages that it's using. It's a little bit more complicated than this because of sharing, because multiple processes on the device can be sharing memory. So for instance, if you have an app that's calling into Google Play Services, it's going to be sharing some memory, perhaps code memory or other kinds of memory, with the Google Play Services process. And then we can ask, how should we account for this shared memory? Is that part of the responsibility of the application? Is that memory impact something that we should care about? And there's a few different ways that you can approach this. One is to use what we call resident set size, or RSS. And what this means is when we're counting in apps RSS, we're saying the application is fully responsible for all the pages of memory that it's sharing with other applications. Another approach is called proportional set size, PSS. And in this case, we're going to say the app is responsible for those shared pages proportional to the number of processes that are sharing them. So in this case, 2 applications or processes sharing these pages, the application will say is responsible for half of them. If there were 3 processes sharing the same memory, we would say the application is responsible for 1/3 of them, and so on. And then a third approach you can take is called unique set size, where we say the application is not responsible for any of its shared pages. Now, in general, which approach to take really depends on the context. So for instance, if those shared pages were not being used in the Google Play Services app until your app called into Google Play Services, then maybe it makes sense to say the app is responsible for all of those pages. We want to use RSS. On the other hand, if those pages were sitting in memory in the Google Play Services process before the app called into Google Play Services, they were always there, the app is not bringing them into memory, then we wouldn't want to count them. USS would be more appropriate. In general, we don't have access to this high-level context to know, at least at the system level, so the approach we take is the most straightforward one, which is proportional set size with equal sharing. And one benefit of using PSS for evaluating an application's memory impact, especially when looking at multiple processes at the same time, is it will avoid overcounting or undercounting of shared pages. Okay, so use PSS for your application's memory impact, and you can run this command, adb shell dump sysmeminfo-s, give it your process name, com.example.richard, or whatever it is, or you can give the process ID if you happen to know that, and it's going to output something like this, an app summary view of the application's memory, and at the very bottom there's a total, and that number is the application's PSS. This is adb shell dump sysmeminfo-s. Okay. Now, let's say you do this, you figure out what the PSS of your application is. There's a very interesting question to ask. How much memory should your application be using? Because, you know, I say earlier, if we use a lot of memory, that's bad because low memory killer kicks in, but we're actually using memory for a reason. We're using it to provide features, to provide user value, to provide, you know, delightfulness. Everything that makes our app great is going to be taking up memory. So we have this trade-off between user value and memory. That's what I'm showing here in this graph, the trade-off space. In an ideal world, we're kind of up and to the left on the graph, where we're providing a lot of user value without very much memory impact at all. But in practice, this is going to probably be technically infeasible because you need memory to provide value, and there's only so much value you can provide with a limited amount of memory. On the other hand, the other extreme would be if you're using a lot of memory to provide not much value. And I think it's safe to say this is not a great app because it's providing too much memory, using too much memory. Unfortunately, my slides are not showing up right, but imagine a curve on which there's too much memory for this app. It's not worth it to the user to use. Ah, there they go. Wonderful. Next, we can look at this corner of the graph where we're not providing too much user value, we're not using too much memory. We can say this is like a small application, maybe your desk clock app. And at the other end, we can have apps that use a lot of memory to provide a lot of value. These are large applications, maybe a photo editor, something like that. And we can say, well, what's better, a small app or a large app? In this case, they can both be useful. Except that when I've said that an application is using too much memory, that really depends on what kind of device you're running on. If you're running on a premium device, it can support much larger applications. But on a smaller device, an entry-level device, maybe this large app uses too much memory to make sense on that. So really, I should be drawing a line and say too much memory depends on the device. Premium, mid-tier, and entry-level might not support that large app. For better or for worse, what I see happening often is over time, as you develop your application, you tend to add more features. It tends to take more memory. So you tend to go up and to the right in this graph. Now, this is actually good for mid-tier and premium users because they're getting more value, more bang for their buck memory-wise. But in this case, it's a little bit unfortunate for the entry-level device user because while he could use the older version of your app, you've now added so many features and it's using so much memory that it just doesn't work as well on their device. So the points that I want to say here, the takeaways, anything you can do to improve your application's memory efficiency is good. So if you can move to the left on this graph, so less memory use without sacrificing user value, that's great. And just be aware that when you're adding new features, while it can be good for mid-tier and premium device users, there might be a negative consequence for these entry-level devices. Okay, there's something wrong with this graph. Does anyone know what it is? Well, let me see. The problem that this graph is, it's suggesting that an application's memory use is one number. So you give me this application, and I can tell you it's PSS. But in practice, that's far from the case, because an application's memory impact depends on a whole bunch of different things, such as the application use case, the platform configuration, and device memory pressure. And so this is important to be aware of when you're testing your application's memory, perhaps testing for regressions or to see if an optimization is working, to make sure that you're testing the application use case you care about, and you're controlling all of the other parameters so that you're doing a proper apples-to-apples comparison. Let me go into a little bit more detail. So how does an application use case impact memory? What I've done here is I started using Gmail, and I've switched to different use cases in the application over time. So every 20 seconds I switch. I started by viewing the inbox. It's using just a little over 100 megabytes PSS. Then I switched to looking at an email that had some text, uses a little bit more memory. I switched to looking at a different email, this one time with pictures, that uses more memory. Then I started to compose an email, used a little bit less. I stopped using the app, and then it used less memory. So you can see here that depending on the application use case, memory impact varies quite significantly. And it doesn't necessarily make any sense to compare your application's memory from point A and point B, because these are different use cases. Okay. Application use case is a pretty straightforward factor. Something that's less obvious is that your memory will change a lot depending on what your platform configuration is. So what I'm showing in this graph is I've picked one of those application use cases from the previous slide, Gmail, looking at an email with pictures, and I've run it on a bunch of different devices. So a Nexus 4, Nexus 5X, Nexus 6P, Pixel XL, and also on a number of different platform versions, even within the same device. So for instance, for the Nexus 5, I ran it on Android M, N, and O. And you can see that there's quite a variation in how much memory this application use case is taking up. This comes about because, well, for different devices, we have different screen resolutions, different screen sizes, which means bitmaps take up different amounts of memory. You might have different platform optimizations on the different devices. You might have a different Zygote configuration, different runtime configuration. It's running your code differently. And so there's a lot of different factors going on here, which mean when you switch to a different platform configuration, you're going to get different memory use. So I would say when you're testing your application's memory use, try as hard as you can to use a consistent platform setup, the same kind of device, the same platform version, and the same scenario of what's running on device. And now there's a third case I want to talk about, which is pretty interesting because it's a little bit counterintuitive, which is an application's memory impact depends on the memory pressure on device. So here what I've done is I've taken Chrome application, and I started running it on a device that had plenty of free memory. And then I set up some native process in the background that's going to slowly use up more and more memory on the device so that I can see what happens to Chrome when the device gets under medium memory pressure or high memory pressure. And we can see when there's plenty of free memory on the device, so low memory pressure, Chrome's PSS is pretty flat, except for that little spike, which is probably some variation in app use case or the platform. When the device gets under enough memory pressure, that K-swap-D kicks in and starts to reclaim cache pages. Well, some of those pages that it reclaims are going to be from the Chrome process, and that's going to cause Chrome's memory impact to go down. Its PSS is going to go down until eventually, if the device has so much memory pressure, the low memory killer is active, and it decides it wants to kill Chrome, then PSS for Chrome is going to very quickly drop to 0. So what you can see here is that even for the same application use case, the same platform configuration, we have a wide range of PSS values we might get. And so you have to be a little bit careful. Imagine I've come up with this optimized version of the Chrome APK. and it has this kind of lighter blue line for the memory profile. I'm confident that this is an optimized version of the APK from a memory standpoint, because for every level of device memory pressure, it uses less memory. But if I'm doing a test, and I sample the PSS of the original Chrome version at point A, but I sample the PSS of the supposedly optimized Chrome version at point B, and I compare, and I say, oh, well, A is less than B, so A has less memory. I might falsely conclude that the original version of Chrome is better than my optimized version. So you really have to be careful when comparing PSS values to make sure that the device memory pressure is the same, otherwise you can get these funny results. My advice, because it's pretty hard to control for device memory pressure, is to run your tests on a device that has plenty of free RAM, so that there's a low device memory pressure, and you can see the PSS numbers will be much more stable in that area. Okay, so we talked about why you want your applications not to take up too much memory, how you can evaluate your application's memory impact. Let me now give you some tips for how to reduce your application's memory impact. And the first tip is check out Android Studio's memory profiler. Profile your application's Java heap. This is going to give you a ton of information, useful information about the Java objects on your heap. So where they're allocated, what's holding on to them, how big they are, pretty much anything you want to know about the Java heap you can see from this. My tip for you is to focus on the app heap. So if you open this up in Android Studio, you'll see 3 heaps. One is a Zygote heap, one the image heap, one the app heap. The image heap and the Zygote heap are inherited from the system when your application first launches, so there's not much you can do about that. But definitely, you can do a lot on the app heap. I'm not going to go into a ton of detail on how you would use this tool, or actually not very much at all, because Esteban is going to be giving a talk tomorrow at 12:30 on exactly how to use this tool. His team built the tool. He's going to be talking about how to do live allocation tracking and heap analysis. So I highly recommend you go check out that talk tomorrow at 12:30. Okay, so you say, Richard, you've told us that we should care about PSS, that's our application's memory impact. You just told us we should use the Android Studio's memory profile to profile the Java heap. But if we look here, we see, well, the Java heap's not actually all that much of the overall memory impact of the application. What about all the rest of this memory? What should we do here? This is tricky because most of these applications, or allocations, sorry, are originating deep within the platform stack, the Android stack. So if you want to know about them and really understand them, it helps to know a lot more about, say, how Frameworks is implementing the view system of resources, or how the native libraries, fonts, and SQLite and WebView is working, from the Android runtime, how it's running your code, from the hardware abstraction layer, how graphics is working, all the way down to virtual memory management in the Linux kernel. By the way, I live in the orange block in the middle, the Android runtime. That's where I am in the stack. So you might ask, okay, so this memory is coming from the platform or within the platform. Should we be using platform tools to diagnose this memory? For instance, if dump_systeminfo-s, that summary view isn't enough, you could try running dump_systeminfo with -a to show basically everything you can see from a platform perspective about your application's memory use. This will give you a much more detailed breakdown. For instance, instead of seeing your code memory regressed, you can see, is it because my .so memory mappings have regressed, or my .apk or .dex memory mappings have regressed. It'll also show you a breakdown of the different categories of memory, so private, clean, shared, dirty, and so on. Private dirty memory is like the used memory I was talking about at the beginning. Private clean memory, the clean suggests it's like the cache memory that also lives on disk. So you could use dump system.info. If that's not enough detail, maybe you see, okay, .apk mmap regressed. There's this tool called showmap you can do, run on your application, and it's going to give you an even more fine-grained breakdown of your memory mappings. And it'll actually give you specific files that are being memory mapped in your application. And this can help pinpoint what files might have led to regressions. In the platform, we have a heap dump viewer that I've developed, experimental heap dump viewer called AHAT that tries to surface more platform-specific things. You could try using that to learn more about your Java heap, though Android Studio's memory profile will have all the same information. And then we also have on the platform something called debug malloc. This is where you can instrument your application so that every native allocation it makes, it's going to save a backtrace, a stack trace to that allocation. You take what we call a native heap snapshot of your app when it's running instrumented. And if you have the symbols, you can desymbolize the stack traces, and you can get native stack traces for all of your native allocations. This has quite a bit of overhead at runtime, and so it can be a little bit tricky to work, but it provides a lot of insight into the native heap. So we have these platform tools. Should we use them? Can we use them? Well, certainly you could. They're all available, but some caveats with these tools: they tend not to be well supported. They have very clumsy user interfaces, as you just witnessed from my snapshots. This approach requires quite a bit of deep platform expertise to understand, for instance, what's the difference between dex mmap, vdex mmap, oat mmap, where are these things coming from, for instance. You might need to have a rooted device, such as in the case for showmap and debug malloc. You might have to build the platform yourself if you want to get your hands on AHAT or the symbols that debug malloc needs to desymbolize. The numbers tend to be pretty noisy because you're looking at memory at a page level. And a lot of the memory use you'll see from these tools is kind of outside of your control anyway. So you might see zygote allocations, runtime allocations that aren't related to your code. So I don't think that this is the best use of your time to try and use these tools, though by all means, go ahead and try them out. I'm going to give a bit of a different suggestion, which is if you want to improve your overall memory use, do two things. One, profile your Java heap using Android Studio's memory profiler like I showed before. And two, reduce your APK size. And let me tell you why I think this is a reasonable approach for you to take to reduce your overall memory impact. First is that allocations that are outside of the Java heap, many of those are tied to Java allocations. So your application is calling into the Android frameworks, which is calling into native libraries under the cover, which is doing native allocations or even graphics allocations, whose lifetime is tied to Java objects. For instance, just to give you a sampling, in Java, on your Java heap, if you see these kinds of objects, so a SQLite database, web views, patterns, those all have native allocations associated with them. If you see a dex file object, that's going to have .dex mmap, .vdex, .oat mmap associated with it. If you have thread instances on your Java heap, that's going to be associated with stack memory. And if you're using bitmaps or sometimes surface views or texture views, that can lead to graphics memory use. And there are many others. So if you're focusing on your Java heap, you're worried it's not going to help anywhere else. That's not true. Optimizations on your Java heap are going to help with other memory categories as well. I am trying, as part of my job, to surface better this information about these kind of non-Java heap allocations. And you start to see that if you look at Android Studio's memory profilers, it'll report a number called native. And I just want to let you know this is kind of an approximation or a suggestion of some of the non-Java memory that might be associated with a Java object. take it with a little bit of a grain of salt, but it works really well for surfacing the memory impacts of, say, bitmaps. Okay, my second suggestion was reduce your APK size. And why do you do this? Because a lot of things that take up space in your APK take up space in memory at runtime as well. For instance, your classes.dex file is going to take up space on the Java heap in terms of class objects. It's going to take up code memory for the memory map dex file. It's also going to take up what shows up in private other in the app summary view, runtime metadata, representations for your fields, methods, and strings, and so on. If you have bitmaps in your APK, when those are loaded at runtime, the pixel data is going to take up space depending on the platform version or how you've loaded them, either in the Java heap, the native heap, or as graphics. Resources in your APK take up space on the Java heap. Say you have an asset manager object. Also on the native heap, you have a parsed zip file structure that shows up there, and you're going to have code memory for your APK mmap. And .so files, if you're shipping libraries, JNI native libraries with your application, when you're accessing those libraries at runtime, it's going to take up space. So all of these things, if you can shrink them, you reduce your APK size, you reduce your memory size. And I will tell you that measuring APK size reliably is much easier than memory, because for an APK, you actually do have one number for the size. If you measure the APK size for a single APK repeatedly, you will get the same result, very much unlike memory. There was a talk at Google I/O last year called Best Practices to Slim Down Your App Size. I recommend you check that out. That'll give you more advice, more concrete action items you can take to shrink these things. OK, let me do a quick recap of why we care about memory, what I suggest you do to improve your application's memory use. So first, I talked about how as we use more memory on device, the low memory killer is going to eventually kick in. It's going to kill processes. If the user cares about these processes, that's bad. If the device is getting low memory killers running too much, then OEMs won't want to produce the entry-level device. Then we lose those devices, we lose those users. To evaluate your application's memory impact, use PSS. Anything you can do to improve your memory efficiency is good. When you're testing for memory regressions or optimizations, make sure you're targeting the application use case you care about and controlling for the platform configuration. Test on a device that has plenty of free RAM to help control for device memory pressure. And to reduce your application's memory use, do try out Android Studio's memory profiler. Focus on the app heap. Go to the session that Esteban's giving tomorrow at 12:30 to learn more about how to do that. Do what you can to reduce your APK size, and check out the talk from last year on how you can do that. So thank you all for coming. I would love to chat with you more and hear more about the memory challenges you're facing. So you'll find me. I'll hang out for a little while outside after the stage. And you can also find me at the Android Runtime office hours, which are 5:30. So that's just a couple hours in tent F after this talk. Thank you very much.